Hello everyone, Mr. Boltri here bringing you video 3.3, where we're going to talk about Newton's first law. So Isaac Newton was this guy, really good scientist who lived a couple hundred years ago. He discovered a bunch of stuff, including calculus and some laws for motion. But he is actually dead now and has been dead for a while. So I don't really like talking about dead scientists, even really good scientists. I prefer to talk about what we did in class. Because what we did in class was, first of all, we did the bowling ball Grand Prix, and we made some observations based on that. And then we did some observations for the cart on the track, and then we have a PT graph for that experiment too. And then most importantly, science is about recognizing patterns. So we kind of tried to notice what was similar between those two pretty different experiments. And here are some of our major findings. We noticed that the pushes and the pulls cause the object to speed up and slow down. And we also noticed that in the middle, in the no touch zone in the middle, the object kept moving even though it was after we were done, even after the force was no longer acting on it. So we can actually wrap these both up into, let's go back to what Mr. Isaac Newton said a couple hundred years ago. He said, every object persists in a state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. Which is a pretty complicated way to say something that I know many of you have heard before, which is an object at rest stays at rest, and an object in motion stays in motion unless acted on by a force, which is a pretty long way to say something that I found kind of a shorter way to say, because at rest is just a velocity of 0, right? And then in motion is just some other constant velocity. So we could shorten this all, not even use Mr. Newton's complicated language or what you've probably heard before. You can just really get this down to almost as few words as possible. You can say an object maintains a constant velocity unless acted on by a force. So if it's acted on by a force, then it doesn't maintain a constant velocity, means it changes its velocity. But otherwise, it maintains a constant velocity. So if it's stationary, it stays stationary. If it's moving, it stays moving. And then velocity also has direction, which implies further that it doesn't change its directions. But there's one thing that's a little bit wrong with this, because if we think of the example of this implies that a force should cause a change in velocity. But if we think of an example of two kids that are both pushing on either side of a box, so they're both applying a force, but the box doesn't change its velocity. So we have to think about why that is. Well, if one kid pushes to the left, the other kid pushes to the right, and they're even, then the box isn't going to move. But that means that we need to update our law to include the idea that, well, the forces have to be, one of them has to be bigger than the other in order for it to change its velocity. So in order to update the law with some increased better language, I'm going to introduce just 3 new vocabulary words, which I would ask that you write down. So vocabulary word number 1 is the net force. The net force, think about throwing a net out into the water. Even if you're trying to catch fish, if there's trash or lobsters or anything out there, you're going to pull them all in with your net. So the net force is the sum of all of the forces acting on the object. So if there's a force to the left and a force to the right, we're going to add them together. Except the force to the left, we're going to say is negative. The force to the right, we're going to say is positive. So the negative and the positive might cancel each other out. So the net force is the sum, which means you add them all together, of all the forces acting on a single object. So if all those forces add up and they all cancel out, they all add sum up to be 0, we can say the forces are balancing each other out. It means any forces to the left are balancing out any forces to the right because they add up to 0. Same for any forces up and any forces down. And an unbalanced force is when they don't add up to 0. Maybe that means there's more force to the right than there is to the left, or vice versa. So then to update our law, we can say that an object does maintain a constant velocity unless it's acted on by an unbalanced force. Because it's the unbalanced force, let's say this child pushes a lot harder, creating an unbalanced force, then the box is going to experience a change in velocity. So this is a really small, simple, easy way to write Newton's first law, which we can just say is the law that relates force and velocity. But I really like to try to get things down to as simple as possible. So I can actually write Newton's first law in 6 words only, because Newton's first law relates forces and velocity. And if we think about it, balanced forces means constant velocity, unbalanced forces means changing velocity. So if you can remember these 6 words, you're going to remember Newton's first law. But here's the thing about this class. I don't want you to just memorize these 6 words. And obviously you can write them down in your lab notebook, but I really want you to understand how this is related to the bowling ball lab and how it's related to the cart on the track demo that we did. Anytime the forces were balanced, the object moved with a constant velocity, either stationary or just kind of coasting along, like the ball rolling in the no-touch zone in the gym. And then anytime we pushed or pulled the object, either with the broom or with the meter stick or with the weight dragging behind the car, then the object changed velocity, either sped up or slowed down. So hopefully this was a pretty good summary of Newton's first law, and we're going to do some practice problems trying to apply Newton's first law in our next class. So write down any questions if you have them. Please let me know, and I want to make sure they get answered. But until then, go Bears.